this demonstration, you'll learn how to use the mapped mesh technique in ANSYS Fluent. This technique is useful in many applications, such as automotive under-the-hood simulations, where heat transfer is an important consideration. For the purposes of this demonstration, we'll outline a general approach of the setup using a simplified set of vehicle components. Later, we'll review a real application and its use of the mapped meshing technique. This particular geometry represents an exhaust manifold assembly near one of the tires. We want to study the thermal effects of the hot exhaust pipe on the nearby components. The mesh for this problem consists of a mesh for the fluid regions both inside and outside of the pipes. We also created a non-conformal mesh for the solid pipes. Here we have the solid regions that will be affected by the hot exhaust pipe, the small rectangular electronics case and its support bracket, and the drum housing with its corresponding clamps. Here's the view of the solid-solid interface between the drum and one of its clamps. You see a non-conformal interface where the nodes are not matching. Here's the same area with the fluid exposed at the top. There is a continuous prism layer attached to the fluid. For this case, we have set up the materials, the physical models, boundary conditions, and solution settings. For turbulence, we have used the realizable K-epsilon model. For radiation, we are using the discrete ordinate model. For materials, we're using air for the fluid region, and the solid regions are aluminum. The inlet boundary is set to a velocity of 5 meters per second at 300 Kelvin. The outlet is set to a pressure of 0 pascals. The exhaust pipe is set to a temperature of 800 Kelvin. We will use the Mesh Interface dialog box to create the mapped mesh interfaces. I've already set up the mesh interfaces for the solid-solid interface zones, so I'll select the remaining unassigned interface zones. These will make up the fluid-solid mesh interfaces, where I want to model conjugate heat transfer. I can choose one-to-one pairing so that each mesh interface is comprised of only 2 zones. This will reduce calculation expense and limit any needed troubleshooting. I'll enable the mapped option, which is more robust than the standard non-conformal interface, when the interface zones penetrate each other or have gaps between them. I'll enter a prefix that will easily identify these as fluid-solid mesh interfaces, then select Auto Create. Fluent will automatically determine which of the selected interface zones can be grouped together to form mesh interfaces based on their proximity to each other. This is especially convenient when dealing with large numbers of interface zones. I can define a local tolerance to determine the size of the gaps or penetrations that are allowed in each interface. In general, a value of 3 or less is most efficient. Now we can review the various interface mappings. Here we have one of the fluid-solid interface mappings. The word main in the name refers to the name of the fluid. The fluid-solid interface needs to be mapped to its corresponding interface pair. This corresponds to the mesh interface of the fluid that faces the solid clamp, and its matching surface, the mesh interface of the solid clamp that faces the fluid. Here's the mesh for one of the clamps from the drum housing. See how the 2 mesh interfaces overlap? One interface belongs to the fluid, and the other interface belongs to the solid. Here we have one of the solid-solid non-conformal interfaces. The mesh interfaces are similarly defined. In this case, the surface is between the drum and one of its clamps. Some faces belong to the solid drum wall, and some faces belong to the solid clamp surface. This, along with the other surfaces, will use the non-conformal interface technique rather than the mapping technique. We can review the solution settings for the simulation. For example, we use the coupled option, the Green-Gauss node-based method, and second-order discretization for everything except discrete ordinates. We used a current number of 20. We reduced the momentum explicit relaxation factor, and we set various turbulence factors. We can see the thermal effects of the exhaust pipe on the nearby drum and casing. So far, we've demonstrated the basic workflow for setting up a mapped mesh interface for a simple case. More complicated industrial calculations might require the use of journaling and scripting. For example, we have an industrial case using the world car geometry courtesy of PTC. This represents a hot engine and exhaust where we need to see the effects on other components. There are 33 pairs of fluid-solid mapped interfaces. There are 14 pairs of non-conformal solid-solid interfaces. Here we have some results from a full simulation of the PTC world car geometry. For this particular example, approximately 15 man-hours were spared in pre-processing because the conformal mesh did not need to be created during setup. This demonstration illustrates a new and exciting capability that will continue to be enhanced in future releases, but even now provides practical solutions to challenging problems. This concludes this demonstration of using mapped mesh interfaces in ANSYS Fluent.